Hello, everyone. Today is Tuesday, November 25th. This is week 4, day 2 of India Evening and Weekend Platoon. Today, we're going to be covering determining Big O notation. And I believe based on the schedule, Tiffany covered an intro to Big O yesterday. Is that correct?
Yep.
Okay. Sweet. Just in layman's terms, what's Big O?
How resource intensive your algorithm's going to be.
Yeah, how resource intensive your algorithm is going to be or how efficient it is. Very good. So something really important to keep in mind when you're studying Big O here is, at least initially, you don't have to be perfect. You don't have to know this inside and out. You just have to have a general idea of what it is and what's a better algorithm. When you view a couple of algorithms, you can tell maybe you don't get it right away, what exactly the Big O notation is for space and time, but you can definitely say, oh, this one's better than that one at first glance. Does everyone understand that? You don't have to be perfect. Today, we're going to get a little mathy, and honestly, the math doesn't matter that much as long as conceptually you understand what it is. Okay. So determining Big O notation. Honestly, the only time this ever comes into play is in interviews. Like if you're lucky enough or skilled enough, or a lot of the time both, to solve your technical challenges, a lot of the times they'll ask you for the Big O of said algorithm, and they'll ask you if there's any possible optimizations that you can see, and if you can explain them. That's pretty much the only time that you will see this. It's a very important time in your career progression, but you don't really see it. Like when you're at work, no one asks you to Big O of something. So just keep that in mind. Alrighty, introduction. Big O notation is a crucial tool in computer science for just analyzing how efficient an algorithm is. Did you guys talk about space and time at all? Big O in terms of space and time?
No.
Okay. In terms of time is how long does it take to run? In terms of space is how much space does it take in memory? That's it. Just keep that in mind. So when people ask Big O, there's actually two answers. There's space and then there's time. It's very possible that something takes up hardly no space, but is very compute intensive. And there's also very possible that something is not very compute intensive, but it takes a lot of space, right? Both of those are types of resources. And when people talk about resources, ultimately, they just talk about money and how much money something costs. All right, so common Big O notations. Has anyone ever seen this chart before?
Yeah, we saw it yesterday.
Okay, this is like the basic like Big O chart you always see when it comes to computer science. And what's the most efficient algorithm on this chart? It's
log event.
there you go. No, no.
Oh, one.
O1, and that's also known as what? What kind of time?
Constant time.
Constant time. That's by far the most efficient. Ideally, when you're writing any kind of code, you want to be as efficient as possible, simply because it's just saves money. Ultimately, it's really just about money. There's nothing more to it, really. Is the most efficient, and the worst one on here is what's known as factorial time. It's O ahead of that little exclamation mark. So here, that's what this represents. Obviously, green means better, red means not so good. Factorial time, I've never actually seen any algorithm in this. You probably will never see it, just know what it is. This denotes exponential time complexity, commonly with recursive branching. If you guys remember a couple of weeks ago, you'll never use really a recursive algorithm for anything just because it's not efficient for literally anything. Typically what ends up happening if you absolutely need this, a lot of the times, depending on what it is, and if it's not a band-aid on something, they'll refactor the data source. They'll refactor the data source so you can access it in as close to constant time as you possibly can. Because that's ultimately going to make your application performant and cheap to use. So you'll honestly never see these two, the top two. Know what they are, know what factorial time, know what exponential time are, but you're never going to see this. This one you hardly will, sometimes you'll see it, but rarely. Signifies quadratic time. Can you give me the most basic example of something that's O(n) squared? It's when you have two loops that are what?
Nested.
Two nested loops, right? Really, really not efficient at all. All right. And so when we start talking about just a regular loop, which is O of n, right? When you're doing a loop, O of n, what does n represent? Anybody know?
Number?
It represents a number, but also represents. Someone said iterations. Yeah. How many iterations? Right. So this specific algorithm will grow as the number grows or as the list grows. If you have a list of 10 elements, it's going to do 10 iterations. If you have a list of 1,000,000 elements, it's going to do 1,000,000 iterations. Right. The efficiency scales linearly according to input size. Right. And sometimes people think, oh, it's, one loop. Nested loops can't be that much worse. Right? But it actually is significantly worse because it doesn't grow linearly. What's the difference between O of n, a normal loop, and then two loops that are nested? That's not linear, it's what?
Exponential.
Yeah, right. So you're talking not in linear time, but you're talking in orders of magnitude. Does everyone understand that? So humans are actually not very good at thinking about really big numbers. Because it's really difficult and we don't really see it in everyday life. But in programming, you're going to see it a lot, right? I think it might have been the first week when we had class, and I told you that the difference between like your wife that's a great chef and maybe like a 1 or a 2-star Michelin chef, it might be 5x, might be 10x, maybe 15x, right? Most jobs are like that, maybe less than that. Pretty much every job in the world. But in programming, it's just a special type of niche where the best programmer can potentially be 100x better than your average hirable programmer. So in computing, you see it a lot. So when we start talking of, notice how I'm speaking in broad terms because the specifics are not really that important. What really is important that you understand that, hey, this isn't linear. It's orders of magnitude different. As long as you understand that, you're going to be just fine. Right, a slightly more optimal algorithm is O log of n. It represents linear arithmetic time complexity, commonly observed in efficient sorting algorithms like merge sort or heap sort. If you're not familiar with those sorts, don't worry about it. The only thing that I want you to remember about this type of algorithm is a lot of the built-in methods in Python and JavaScript are this time complexity. A lot of them are. Why? I'm not quite sure. But that's the one thing to remember about this. And then O of n is just your basic loop. The thing to really remember about this time complexity is look at everything in a programming language. Understand every single scenario in a programming language that gives you this type of time complexity. Right? I'll pull this up right here. Let's say, can everyone see my screen?
Yes.
All right. Say you have some kind of list that has just some random numbers in it. And you have 4 num in some list. What's happening here on line 4?
Iterating through the sum list.
Yeah, I'm just going to iterate over num list, right? And if I do here, if num equals 3, return true. What kind of time complexity is this? Oh, oops. Sorry, guys. There's more people in here. What kind of time complexity is that?
It's just O(n).
Yeah, just O of n. Why?
Because you're just iterating through a list.
Yeah, you're just iterating through a list, right? And you're ultimately going to check every single element, check if that number is 3. If it is, you're just going to return true, right? Be very, very careful on what your conditionals do. Sometimes people won't know what this conditional does, right? Can anyone give me a function? Can anyone think of a Python function that's a linear search under the hood off the top of your head?
Sort.
No.
In.
Yes. In is a linear search underneath the hood. Sometimes people will do something like this. If man, I don't even write that much Python. They'll do something like this. What type of complexity is this? I misspelled index.
It's constant.
No.
O(n) squared.
Yeah, why, Scott?
Because you're still nested loop because you're doing the for num in some list, and you're also pulling the index for what the item number 10.
Yeah, that's right. So I'd like to show this really simple example because it kind of illustrates my point. Not all conditionals. You have to understand what the built-in methods are in every language, because I gave you that very small nuanced example last time where in Python specifically, can't speak for other languages, but in Python, depending on how you're using it, it's either a linear search or constant time access of a dictionary. And you would have to look at the code to know what it is, right? But depending on what data type it's acting on, the efficiency is different. That's just a very minor and probably my favorite Python example to illustrate this point. Understand Python really, really well, because when you start coding things out, it really pays to know what exactly is happening under the hood, how efficient that algorithm is. Notice I haven't really gotten into any math right now. Right now, it's really just emphasizing understanding the efficiency of algorithms at kind of like this like broad strokes level, right? And yes, this would be O of n squared. This is a loop underneath. This is a linear search. This index method is a linear search, and you have it nested within another linear search. Does that example make sense? Cool. Alrighty, O of log n denotes logarithmic time complexity, common in algorithms like binary search, probably one of the most common search algorithms, which I don't even think that's today. I think that's tomorrow. But we'll jump into it. Oh no, that is tomorrow. So you'll get to play around with binary search tomorrow. And then O of n represents constant time complexity, indicating consistent efficiency regardless of input size, right? How does the dictionary in Python exemplify this right here?
Key value.
Yeah, key value. If I have a dictionary with 10 million elements, but I know the key of the value that I want, I'm not going to iterate at all. I'm just going to grab that key and grab its value. That's direct. It took me exactly one iteration. It doesn't matter that the dictionary had 10 million elements. I'm not going to iterate over it. I'm going to access it directly because I know the key of the value that I'm looking for. In programming, you try to stick to the first three, if at all possible. If at all possible. Sometimes you can't, right? And you go into some of this. Just for reference, most of the built-in sorting algorithms you have in most languages aren't particularly efficient. So just keep that in mind. Yes? Let me give you an example. Let's if I run this, what am I going to get?
One.
Sorted so much.
Either 1 or 10, right? Because whenever it sorts it, it's going to put those two side by side.
Yeah, I got one. If I wanted to get the last element, let's print new list. What is new list? What's happening?
It's sorting them in ascending order.
In ascending order. What if I wanted to grab the last element? What about if I wanted to get the biggest element?
I wonder where it is.
Like,
You're giving
just
it.
going to do -1 on the index, or
Okay, yeah. So if I just do -1, that gives me the last one. If I know that I sorted it, then the last one has to be the largest. This should return 37, right? It does. What's a better way to do this? If you were given a challenge, say, hey, write a function that returns the largest number of a list, how would you do it? I showed you this way. This works. But why wouldn't you do it this way?
could you just do an if and then store the greatest number as you iterate through it and replace the counter or whatever you want to call it with the biggest number as you iterate it through at one time?
You want to walk me through that solution?
Yeah, sure. I would just pretty much go with your sum list and just say if I guess you'd have to initialize a variable first. So
Okay.
you could just say big
I'm
num.
writing the function. We're going to start from the function. We're going to just write the entire
Mhm.
function. Okay, look, is that you, Logan?
Okay.
Who is that?
Yeah.
All right, go
It's
ahead.
Logan. So are you going to use the sum list above because you named it sum array?
Oh,
Or are you
yeah,
going to
sure.
pass an array? Okay.
Yep.
So I would just say big num, like our initialize a variable called big num, set it
Mhm.
to 0.
Mhm.
And then next line, if we're gonna have to do if I in some array
You're missing something. We need to do what?
while for I. Oh, yeah,
Yeah, we need to iterate over the
Oh
sum
yeah,
r, right?
for num, yeah, for num and some array, yeah.
Uh-huh.
Yeah, if num greater than big num,
Mm-hmm.
big num equals num.
Mm-hmm.
and then have it
Return
return.
big
Yeah.
num, right?
Mm.
Yeah. If I wrote this, I know they didn't write this as a function because I was lazy, but if this was a function, what's the time complexity of this? Anyone know? I don't expect you to know this, by the way, but it's right there. And login, right? What's the space time? What's the time complexity of this one?
It's 5, or well, actually not 5, and it's constant
No, it's not constant. It's O of.
because it's got to iterate over everything to sort the list.
Yeah. So what is it?
I thought that was n, O of n.
Say it the right way. O of n, right? It's not just n. What does n mean? It could be anything, right? This is linear time. This is n of log n time, right? Which one's better?
Well then,
Oh, we know which one's better. Which one's faster?
I guess it
Which
depends
one's
where
more
the big
efficient?
number
Which one's
is.
more performant? Which one's
O of 1.
ultimately just cheaper?
O of 1.
No, out of these two, I think he's asking.
Oh, just hey, give me a second. Give me 1 second, guys. I don't think I was hearing you. Give me 1 second. All right, how about now? Sorry.
Testing.
Yeah, sorry. Sorry. Sometimes when I touch my headphones, they like
Hmm.
mute or something. I don't know. Anyway, so which one's better?
I think log n gets
No,
better over time
no.
with the larger.
O of n.
O of n. O of n is more efficient. It's just a linear search, right? This is a built-in sorting algorithm. They're very rarely the most efficient thing you can write. Rarely, right? Remember I said you try to stick to the first three if you can? Right now, I think sometimes you have to really think about it, especially when you're learning how to code. Maybe at the top of your head, you kind of think about how you're writing it. Eventually, this will become second nature. You'll never write anything that's anything like this. No one really ever thinks about it after, the first year or two. But for right now, it's important for you to think about of why it's important. Again, if you didn't know this, you didn't know exact how to say it or the nomenclature for it, that's totally fine. As long as you understood that this one was better. That's good enough for right now. And you know why. If you forgot it was called O of n log n, totally fine. Right now, broad strokes, understand that this is better. Does everyone understand this somewhat simple example? This code can actually be improved here. Can anyone find the line? There's a hard code somewhere. Someone fix it.
You delete line 12.
Don't delete line 12. You need line 12. You can't hard code 0, right? Because if I give you a list with all negative numbers, that wouldn't work. So what number can we put there?
Couldn't you just like have it be empty or null?
Okay. If we make this null, what happens on iteration one? What's null in Python? Oh, is it none?
None.
Sorry. Sorry, I don't really write Python anymore. There you go, it's none. Thank you. What happens on iteration one if I do this?
There's no comparison, right? So
Well, which line breaks and why?
You're trying to compare two data types.
There you go. Who said that? Nice job, Logan. Star pupil, 1,000,000 gold stars. Line 14 breaks. So it can't be none. It can't be nothing either. It has to be something. So what is that something?
true.
You run into the same problem as stated earlier. Different data types. So it's not true. It has to be integer. It has to be an integer, right? Because then line 14 breaks. So which is it? Can't be 0 because that's a hard code. But it can be dynamic. So you can just use the very first one.
The index of the list,
That
Which one?
0.
0.
Why?
It's the first in the array.
Yeah. Let's just set it there to start off with, and then it will compare every single one after that. Right? There's actually a duplicate iteration here. Does anyone see it? On that loop on first iteration, what's the comparison?
Sum array 0 to sum array 0.
Yeah, so you don't start at 0 if you wrote it this way, you'd start at index.
1.
Yeah, for I in range. And you're thinking, man, it's one iteration, what does it matter? And right here for this example, it doesn't matter. But being able to recognize that is important. What about if you didn't need the first 1,000 elements? No point in iterating over them, right? And you think, Guillermo, that would never happen. Yeah, rarely happens, but sometimes you do have a lot of metadata inside your database that you don't need for a lot of your use cases. So sometimes it does happen. Are we good with this example? Cool. All right, constant time, the goat of all times. Constant time complexity indicates consistent performance regardless of input size, ideal for operations with fixed runtime, such as accessing specific elements, i.e. dictionary, hash map, object, things like that. Weaknesses, limited to operations where the runtime is truly constant, not suitable for scenarios with variable or input dependent runtimes. So that's the thing about constant time. And you're not always going to have like perfectly structured data. So that's not listed as a weakness here, but that happens all the time. Accessing information in constant time. This you index, but you can think of a key value pair in a dictionary. Same thing. So this function just grabs that specific index. Pretty simple. O of log n, logarithmic time, efficient for large data sets. As the algorithm divides the problem space in half with each step, commonly used in binary search and other divide and conquer. It's not a strategy, it's an algorithm, but yes, other divide and conquer algorithms. Weaknesses may not be efficient for small data sets or when the input is not easily divisible. This is a binary search example right here. Binary search has actually, I don't think any, you're probably familiar with this, but binary search only works when what is true. Does anyone know?
The inputs are equal in length.
No, they don't have to necessarily be equal. But whatever you're iterating over has to be in what?
Zeros and ones.
Not quite.
We sort it.
Yeah, it needs to be in order, Brian.
Yeah.
If it's in order, you can divide it into halves every time, right? Like think of a list, 1 to 100, right? And you compare the middle number, right? And the middle number is like 50, but you know that the number is smaller than 50. So if it's smaller than 50, only the first half of the list is in play now, because everything bigger than 50 is too big. It's okay if you're not familiar with binary search, we're going to do an exercise about it. But that's the quintessential example of logarithmic time. Honestly, I can't think of any other one. That's the one that you always see. Not going to get into the binary search right now. I just want to go over all of them first, but then we can run through that example. Linear time. We went over it. It's the famous loop example. This is in terms of time, this is O of n. In terms of space, does anyone know what it is? You use the same nomenclature for time and space.
O of n log n.
No. How much space is this function taking up? You've probably never been asked that question before. But let's start there. How much space is this function taking up?
Well, it depends on
terms
how
of
big the array is.
Does it? The size of the array affects the time. It doesn't affect the space at all. Let's see. I think this is important, so we're going to do this. Oops. And do this. This is the thing in question, right? Let's do two of them. This is, why does that do that? Okay. Oh, I don't think I copied it properly. Okay, cool. What does this function do? Just what does it do?
Adds all the numbers in the array.
It adds all the numbers in the array. Right, so if R was 1, 2, 3, 4, this would give us what, 10? Yes? Yeah?
Yes.
Okay. Let's do linear. What does the function on line 12 do?
Multiplies each number in the list by 2 and then appends it into a new list.
So it returns a list with a bunch of numbers, right?
Yes.
Okay. Does this function grow? Does the result grow dependent on how big the array is?
Yes.
Okay. What's the time complexity of this?
Is that n squared?
No?
I think it's just N.
Is O of n. That's the time complexity of this function. Okay. What's the space complexity of this function?
Would it be
It's
N
also
too?
O of n.
Yes, it's also O of n because the space is going to grow. You're going to need more space if that list keeps growing. That's directly proportional to the input of the function. Right? So this is O of n. Both of them are O of n. Okay. This one is O of n for time. What is it for space? We haven't touched this, so I don't expect you to know, but just based on this example, it has to be what?
O of 1.
Yes.
Okay.
Why?
Always got one return. It's only one output, no matter how big it is.
There you go. Is that you, Nicholas?
Yes.
Okay. That's the reason why I was trying to show you this example, right?
That makes perfect sense that way.
There you go. Good. I got one. Good enough. Understand this concept right here. If you just understand, hey, what is the output doing in relation to the input? Is it not growing at all? O of 1. Is it growing linearly? O of n. Is it squared, quadratic? O of n squared. Is it exponential? O of 2n. What is it doing? If you understand that idea, you understand big O conceptually, and then the rest, the nomenclature, the details and nitty gritty, that will come later. But if you just understand that, you got the bulk of it. Questions about this? Okay. What's a very simple way to think about big O? I just said it earlier. I just want someone to say it again.
Space and time.
Yeah.
Worst case scenario.
Yeah, but you guys are just saying words that don't mean anything. I'm not trying to trick you. I just want you to explain it in layman's terms. What's your function doing in relation to the input? How many iterations? How much space? What's the relationship between input and output? Is it a constant relationship? Is it a linear relationship? Is it a quadratic relationship? Is it exponential relationship? What is it? That will tell you everything that you need to know. I hope that makes sense to everybody because that's really the whole concept. Okay, cool. Alrighty, and the rest are just details here. I don't want to say just details, also really important, but conceptually, I think you need to understand it first. And after that, this all starts to make sense. All right, we talked about linear time, quadratic time. We talked about the infamous nested loops. There are some optimizations that you can make with nested loops. This is one. I'm not going to get into it because I don't think it's really that important. But just know nested loops, you're going to be O of n squared or worse. N log n would be something like a merge sort or a heap sort. A lot of built-in methods. That's the main thing you need to remember. A lot of built-in methods. that this one really famous in divide and conquer algorithms. Not really anything else I want to touch on that. Conclusion, understanding the strengths and weaknesses of different big O notations is crucial for making informed decisions in algorithm selection. Consider the nature of your data, the size of your data set, the specific requirements of your problem to choose an algorithm that balances efficiency, simplicity. The appropriate choice may vary depending on the context of your application. That's more of a fluffy answer. It's always at work, at the very least, is always going to come down to whatever the most efficient is because it's the cheapest. And very rarely you'll see a lot of these. I mean, you'll see them in like coding challenges, right? Before, when you're applying to a job, you'll see these. But at work, you hardly will never see these. You'll always just see this. Does everyone understand why? Because they're just what?
Cheaper.
Efficient
Yep.
and cheap.
Yep, cheap. That's it. Efficiency doesn't even matter. It's just cheap. And I know it's really difficult right now to really understand, well, how cheap? You have to understand even, like, I'll give you an example. One of the very first applications that I worked with at DRW was a really small internal application, but that internal application produced hundreds of thousands of logs an hour. So you're talking about like millions of logs a day. And that was like a small-ish application that was internal facing. It wasn't even customer facing. So imagine a really big application, right? You're talking about millions of logs probably every couple of minutes, depending on how big it is, right? Like the observability logs of like Netflix or like or Hulu or any of those big streaming platforms got to be crazy, right? You're talking about millions, maybe every couple seconds. I think Netflix has like 200 million worldwide users or something like that. Someone correct me if I'm wrong. Something crazy like that, right? Yes? Cool. All right. That's a big concept of a big O. I want to look at both of your assignments just briefly. This is going to be the very first one. It tells you to read these two things. So definitely, like these two things, big O notation explained by a self-taught programmer. They're actually pretty good. Give them a chance. They're just going to reinforce kind of the broad strokes that I gave you earlier. So those two, and then it gives you your second assignment is this one. And I wanted to kind of go over this a little bit together. It gives you a bunch of exercises and see if you can kind of figure out what is the big O notation. I'm going to try to give you a couple of tips. Actually, just one big tip that really helped me. So let's look at this. Does anybody know what this is? Just in grand scheme of things, this is just a function, right? Yeah. A polynomial is just a function, whatever. Ultimately, it can be graphed, right? When you look at this, really a big thing about big O is understand that the exponents will dominate everything else. What does that mean? When you look at an equation like this one, you've probably never seen this equation before unless you clicked on the assignment today. I haven't looked at it until like 3 minutes ago. When you look at this, you can pretend that everything drops except for the biggest exponent. Let me give you an example. You look at this, the 2n drops, the 3 drops, the -1 drops. What's the big O of this equation?
Oh, n squared. Okay.
Oh, it's an n squared.
Does
N
anyone
squared.
understand? Yes. Does anyone understand conceptually why that is? Which is actually the main point I'm trying to get at. Why does everything drop except for the biggest exponent?
So you're looking for the worst case.
Oh, yeah.
Because it defines the function. So like, so for example, a quadratic is a quadratic no matter what. N squared is n squared. It doesn't matter how much your magnitude is or your 2n. So like in math, if you have a cubic function, your cubic function is a cubic function no matter what. You can say 2n cubed minus 4n minus 3, whatever it is. It's still a cubic function, right?
Yeah, but that doesn't mean anything. You didn't say anything. I want the simple term of why does the big exponent dominate? I'm not looking for any kind of mathematical explanation. I just want you to conceptually understand why. That's it. And then lesson over.
It's because once you drop everything, the right side of that equation is heavier than the left side of that equation. So your output, so you're still going to be using more to get the same amount of information.
You're walking the line of the answer. All right. If anyone ever took calculus, this is a limit. At infinity, what does the function do? Right? At infinity, which one element dominates the function? The n squared.
I was going to say that, but you said don't be mathematical.
It's not mathematical. I just say, hey, this one dominates the. Brian, stop, dude. Get out of here.
But
You're making me mad,
I've
bro.
taken calculus, and I was going to say if you increase the number to infinity, is all the other terms would be nominal.
Yes. So what is the time complexity here?
O of n squared.
Just like that. When that number, or you could have just said, hey, when that number gets really, really big, all the other numbers that are not the biggest exponent, right, pale in comparison, right? It's like throwing a cup of water into the ocean. It's irrelevant, right? Yes? Or you're stuck 5K at the blackjack table. What's another 400, right?
Mhm.
Maybe that one hasn't happened to you. All right. Definitely read this. If it gets a little too mathy for you, I wouldn't dwell on it too much, honestly. I would, if this gets too mathy, I would actually just go to the examples and see if you can try to figure out the examples without reading too much into it. Let's see. Let me see. Let me give you another good one. Here's another good one. Right here. Big O of a particular algorithm. Let's look at this one because this one's a little tricky. Does anyone know how to read this? This is log base 2 of n equals what? And a log is really just the inverse of, this was in the lesson though, I didn't go over it. A log is an inverse of a what? An exponent. Right. So this is saying, right, how many squares of what number would it take to get to n? Right. So how many times would you have to divide it by 2 to get to this specific number? So given, and this is kind of an interesting one, given it takes 2 seconds to complete an algorithm with 3 million inputs, how long would it take for 4 million inputs?
Two seconds. 3 million.
That'd be 4. Yeah, I'm guessing delta 4.
Anybody have a different answer?
I did this earlier and I got it wrong. I guessed every single one except the answer.
So what's the answer? So what's the answer?
I
So what's the
think,
answer?
I think it was A.
It's A?
I think so.
I don't think it's A.
Oh shit. See, I got it wrong again and I've already done this.
That's impossible if you tried all of them.
Yeah, you got to get one right. Statistically impossible.
2.04, can anyone tell me roughly why?
Two seconds.
Don't need the math. I just need the conceptual answer.
Because I think it's the way log is shaped, because log approaches an asymptote once it gets large enough. So it just the number gets smaller and smaller, or the outputs get smaller and smaller as you get larger and larger.
Now, give me a more basic definition we can all understand.
You increased less than half. 3 to 4 is a smaller jump than 0 to 4 or anything else.
Yes, that's it. Notice how Scott's answer didn't involve any math at all. But the way that he described it tells me he understands what it is. Could he probably do this math problem? Maybe, maybe not, but that's irrelevant. He answered my question correctly. when you're having every time, he knows that, hey, it only took 2 seconds for 3 million to 4 million. It's not going to take anywhere close to that. Right. So it has to be a fraction. And I picked the smallest fraction.
Why you pick the smallest?
The smallest fraction after 2 seconds, right? Because it takes 2 seconds for 3. Here's a good one. This one I think you guys will be able to get. And I think actually this is a better example. Let's say it takes 2 seconds for an algorithm to complete with 3 million inputs, right? How much time would it take for 10 million?
.2.
Why do you, yeah, who said that?
I did, Nicholas.
Nicholas, yes, that's right. Why?
Because 10 million is more than 3 times as much as 3 million inputs. So if it took 2 seconds, then you gotta have something that's bigger than or closer to 6 seconds, being that it's gonna take 2 seconds for each 3 million.
Yeah.
And then,
so
and then a little bit more than that. So
there you go. So logic has it. Well, it took 2 seconds to complete an algorithm with 3 million. Okay. 3 million, 3 million, 3 million. That gets us to 9 million. That's 6 seconds. Why is my logic flawed right there? So I'm thinking it should take 6 seconds or more than 6 seconds. And that's not right. Why?
Because that would be linear. And
there you go. Yes, it's not linear. It's logarithmic. Right? And a simple way to think about it is this. Look at 10 million. Divide it once by 2 is 5. And if you divide 5 again by 2, it's 2.5. Right? So you know you're looking at somewhere around 4 seconds.
It's proportional too. It's proportionality.
It's not proportional. Proportional and logarithmic are not the same.
No, I mean, I'm not saying that the actual shape of I'm not saying the log is proportional. I'm saying that the times that were given is proportional. So like
yeah, in a weird kind of way, yes.
2 is to 3 as 10 is to n, and then you just solve the proportionality problem. You get an exact number.
Yeah, but again, that would be linear, right?
Yeah, not quite. Not quite. I kind of understand what you're saying.
I've done like a million of these. It's direct proportion. It's a proportionality.
No, it is not. An exponent is not a proportional.
Okay.
It's orders of magnitude. That's like saying
I don't think you understand what I'm saying, but that's fine.
I don't think what you're saying is right. That's what I think.
I don't. Okay. I mean, whatever. I mean, you're the teacher.
What you're reminding of, this is probably a stretch here, but the Richter scale. Anybody familiar with the Richter scale? Someone tell me briefly what it is.
Earthquakes.
Yeah, earthquakes. Can someone tell me the difference between an earthquake that's a 7.0 and an 8.0? What's the difference?
Magnitude.
What makes the ground shake more?
Separated by like a number, right? This like factors of.
Okay, how much
Eight
bigger?
is larger than
All right.
7 by
guys, no one has to tell me that 8 is larger than 7. I know that. Okay. How much bigger is an 8.0 earthquake than a 7.0 earthquake?
1.0 bigger.
In terms of like power. Does anyone understand what I'm trying to get at? Some people think, oh, earthquake was 7.0 or it was 8.0. They're the same earthquake, right? They're kind of close, but they're not close actually. Can anyone tell me why? Does anyone know? All right.
Because it exponentially grows.
Yeah. So when people talk about the difference between a 7.0 earthquake and an 8.0 earthquake, it's a magnitude of 10. That earthquake was 10 times more powerful. It wasn't slightly more powerful. It was an order of magnitude more powerful, right? That is not the same thing, and in no way proportional. It's a logarithmic scale. Just a random example. I know you guys don't care about earthquakes, and neither do I. Although, has anyone ever felt an earthquake?
Yeah.
Does it?
Yeah.
Is it the scariest thing in the world?
Yeah.
Yes.
Especially when you're high up in a building.
Yes. If anyone never felt an earthquake, it feels like the house is going to come down on top of you. And I felt like I think I felt the smallest earthquake that could possibly be recorded in Chicago years ago. It was so weak, it barely registered, but I was awake at the time and I felt like the house was going to fall on top of me. I can't imagine what a real earthquake feels like. Okay. Cool. All right. Yes. All right. So for assignments, sorry, I've been rambling. I would read these two explanations and walk through these examples. And the last thing I would do is, I think this specific article might get too mathy. If it does, I would just go to these questions and see if you can reason them out. The main thing to keep in mind here is conceptually, do you understand, right, the efficiency of algorithms? Now, if you already got that down, Pat, definitely work on the nomenclature and tell me, hey, what's the difference between O n log n and O log n, right? What's the difference? Questions?
Yeah. So quick question. This isn't going to be on the
Yeah.
exam, right?
No. Great question,
Okay.
though. No.
Will this be on the second exam?
I don't think Big O's on any exam.
Oh, okay.
Yeah, Big O's not on any exam at all. It's, again, you're not gonna really run into it. You're gonna run into it in your technicals sometimes. But that's it. Like, you don't run into it at work. I mean, those top three algorithms, I mean, it's good to know about them, but you're never going to use them, right? It's going to burn a bunch of compute for no reason. No one's going to do that. It's just more of a conceptual thing. Like, hey, understand it and understand why, nested loops are bad. And the examples that I gave you, understand that, hey, if you're using built-in methods inside of a for loop, that's a nested loop. Do you understand that? If you do, refactor your code. Right? Here's a good example that actually happens more times than you would think. But you haven't got into APIs, but sometimes people will do like a finance app is really popular. They'll ping an endpoint, but they'll have it in a nested loop, and they'll have an endpoint that only has you can only do 1,000 calls for free, right? And they'll have it in a nested loop, and they'll run it 3 or 4 times as they're developing their application, and then they're out of their 1,000, and they have to pay to get more, pings on the endpoint. And they're like, oh, I only pinged it 6 times. No, dude, you pinged it 60 times, or you pinged it 600 times. That's why you're out of credits or whatever. So I do see it in personal projects every now and then. People don't understand that their algorithm is not very efficient, so you're expending way more compute. Make sense? And right now, in the grand scheme of things, right now it's just Big O for the sake of Big O, right? But eventually, right, when you get to your job and you get into developing, developing APIs are pretty cool. Developing real world applications, you get into a whole idea of of throttling certain requests or just refactoring some of the data that you had because it's not very efficient to access it depending on what the user needs. So that's ultimately what happens. Like I said earlier, typically you won't use those bad algorithms simply because a lot of the times you just refactor your data. That's going to be more efficient and ultimately probably cheaper. All right, that's all I have. I know I rant. Oh, I didn't go that long, only like an hour. So let's take an 18-minute break, and then we'll come back at 6:50 breakout rooms. And really, the main thing that I want you to do first is really just read those 2 articles, and then work through some of the questions in that second assignment. Does that make sense? Cool. All right, I'll pause the recording. Oops. All right, guys. Any questions so far? Big questions, small questions, or everything's more or less making sense?
Yeah, I mean the math's not there, but I get the concept of it.
Good. That's kind of where we all should strive to be by the end of tonight. All right, if there's no questions, if there is or something arises, definitely stop me. I'm just going to go over this first part relatively quickly. The explanations are there, so I'm not going to explain anything that is already there, but I will go over it just very briefly. So the first one is just an example of what?
O(n) squared.
The first one? Not quite.
It's O(n), right? Or O of n?
Yeah, it's just O of n because you're just looping item in array and you're checking every single element, right? If the item is bigger than value, you return false. And it checks every single element until condition that if statement is true. If it's never true, it just returns true, right? O of n. What's this known as? Anyone remember? I mentioned it a while ago.
What was the question?
What is this known as? No, there's no else statement here.
Function.
Return. I don't get the question.
Linear.
It's just an implicit return, right? There's no else. Hey, if this isn't true, then
Oh.
when all the code finishes, right, just return this thing, this Boolean, right? Keep that in mind. Second one, these are just two loops, it looks like. Actually, it doesn't tell you what customers, but let's just assume they're actually, we can't assume that they're the list. What are they? What's customers on snippet 2?
An array.
They're what?
Would be parameter for that one, or like an array.
Mary.
No.
Okay.
We're looking at snippet 2. I'm just asking what data type is customers?
A dictionary.
Yes, a dictionary. Not trying to trick you. I'm never trying to trick you. Look at snippet 2. I just, without really looking at it that much, I said, hey, just assume this is a list. I was actually wrong. But just looking at it, you know it's a dictionary because it's accessing a specific key named name and country. So I know for sure that customers has to be a dictionary, right?
I don't want to make it anymore. We got used to it for a while. Hey, Jordan, if you just make it and it goes away.
Yeah. Hot mic.
Out, Mike. I actually screwed up that explanation. Look at this code again. I screwed that up. Did anyone catch it? I explained it wrong. I'll ask again, what is customers?
Dictionary.
No, you're just repeating what I said. I said I screwed up. Someone correct me. What is customers?
Class.
Customers appears to be a list. Customer appears to be a what?
An item in the list.
No. What data type is customer? It's a dictionary, right? Customer is a dictionary. This is a list of dictionaries. Notice I screwed it up twice. Look at it, really try to figure it out because I am human. I just half-assed looked at it and I was like, oh, this is what it is. No, it isn't. It is a list of dictionaries and customer. I'm accessing name and I'm accessing country. Both of these are linear searches, right? And you have two unnested loops. So it's just O of N, right?
Mhm.
A very common thing that I see with new programmers is they'll tend to, when they need two loops, they'll always nest them. And then I'll always ask, do they need to be nested? And they don't know the answer to that. They don't always have to be nested. If you can unnest your loops and accomplish the same thing, space and time complexity says do it. It's a more efficient algorithm. Yes?
Can you say that last part again?
Yeah, a common mistake that I see is when people need two loops when they're early on in their programming journey, that they will nest them. But don't nest your loops unless you absolutely have to, knowing that it's not a very efficient algorithm. Here, you have two loops, but they're not nested. That's still O of N. You could have 10 loops that are not nested. That's still O of N, right? Worst case scenario is still
Yes.
O of N. Okay, really important to keep that in mind. Okay, cool.
And we're saying, and we're saying, like earlier, you had said, the different types of the O of N's. It was like the O notation. There's like a list of most efficient to worst efficient, right?
Yeah,
Did I capture that? And then so like O of N being the most efficient. Am I interpreting that correctly?
no, it's just middle of the road, right? O of N is right here.
The one is the most efficient.
Yeah,
Well,
O of one
one
constant time is the most. I'll ask you this. O of one is how many iterations?
Yeah, because if you don't want to.
one iteration.
One.
Or
I'm going to ask that again. O of one is how many iterations?
is there even iterations? I didn't think there was any iterations with that one.
There is no iterations. It is constant time. It is direct access. There is no iterations. You can't get better than that.
So if we're like looking for a value by index, is that considered O of one?
Yeah, that's actually the very next.
That's the next example.
One. Yeah, that's the next
Oh, my
example.
bad.
This is, there you go. This is O of one. Direct access by index or key value, or key, not value, key, would be direct access, constant time.
And we're saying direct access is because we're saying at index it equals this. So that's
Yes.
direct access of value. Okay, gotcha. I think the gears are slowly turning. Some of the springs fell out on the way, but it's at least turning now.
We're getting there. All right.
Yeah.
Snippet 4 is what?
Cubed. N of 3?
No,
No,
it's
I don't
not
know.
cubed. Close.
Oh, okay. I
One
see.
squared.
1, 4, 1, 4. So yeah, O squared. Yeah, squared. I see that.
Yes, it's
squared.
quadratic. O of N squared. Two nested loops that iterate over array. Don't let the enumerate fool you. It just gives you the value and the index of that specific element if you need it. There's something that's not, look at snippet 4. There's something that's not needed. What is it?
Return.
Say that again. You can unmute, Jose. It's not return. You need return. Everyone look at
Continue.
snippet 4. Whoever just said that. B, was that you?
Yeah.
All right. It is continue. What is that if statement and continue doing?
It's just continuing on. We don't really need it because it'll just go through the next if.
Yeah, just comparing if the two indexes are the same. But here, it's not really doing anything. You could just return true if item 1 and item 2 are equal. If all the loops finished, then just return false, right? Does the same thing. Does everyone understand that?
So yeah, so we really don't need from if index equals to continue. We just take that whole portion out, is what you're saying, right?
Correct.
Gotcha.
All right. Snippet 4, big O of all of n squared. That if index 1 equals index 2, it's actually, I don't really need it. Snippet 4 is snippet 5, sorry. Snippet 5, what time complexity is it?
O(n) squared.
It is O of n squared here for the simple fact that words and endings are the same length. Let's say they weren't the same length. What would it be? You can make up the variable. You can make up the variable names. It doesn't matter. These are the same length, right? On snippet 5. O of n squared I'll take. That's the answer. But
both 3.
yeah, but what if endings was 10 and words was 3? It would be O of. It would just be O of n times n, or whatever two variables you want to use. Remember, we have two nested loops is O of n squared. The first loop is n, the nested loop is n squared. You just multiply them. That's all it would be. So you would multiply this length times this length, and that would be the time complexity. Typically, people use like n and m, but they're just variables like a or b, or I don't know, a and b are like the most common variables.
You're saying the time complexity would be 6? I don't understand.
No, I didn't say that at all. All right.
You multiply,
look at the length.
You said multiply the top, the size of the top times the size of the bottom.
3 times 3 isn't 6. It's 9.
Yeah.
So I didn't say that.
So 3 times 3 is 9?
I'm just catching the last part of what you're saying. Can you explain what you're saying?
So when people say O of n squared, the first n is the outer loop. And the inner loop is another n squared. N times n is n squared, right? If these two things are different lengths, right, it would just be the same thing, just give it a different variable name. It'd be O of n, but not n again, right? Because they're different lengths. N stands for the length of that variable. It'd be n times n, but the variable names here are arbitrary. It could be O of donkey times monkey. Doesn't matter. I mean, don't write that in your code, but the concept is the same. They're just variable names. Or does that make sense?
Yeah, like you wrote in the text, is it O(n) and times O(n)?
Yeah.
Okay.
All right. I hope that didn't confuse anyone. You're just multiplying if they're nested. That's it. All right. This one is just looping over array and it's printing item. That's a pretty easy one. The standard what?
Standard n.
O of n. This one's a little more complicated, right? This has an O of n loop on the outside and then it has a while loop on the inside.
I mean, it's still a loop.
Yes, it is. Any thoughts on this one? This actually kind of gives it to you right here. I told you that a lot of the built-in methods are what? What type of complexity? It's the weird one.
It's
Built-ins.
n log n.
And login. Anytime you see something like that, that's probably a pretty good guess.
I just want to make sure. Okay, so anytime I see something like that, so there is a row and there is a column here involved in this loop, correct? From the range and length. The I is the row and the J is the column. Is that how it works?
No. I and J are just index values at that specific iteration. That's all it is.
Okay.
I haven't given you a problem with like matrices or anything. Then you would get into like rows and columns, but that's not here.
All right, cool. Thank you.
Snippet 8. What is snippet 8?
That would be
It's also nested. So I see built-in functions.
Don't overthink it. It's two loops, right? So it's O of n squared. Here's the bonus question though. What's happening here?
it's like
I can't think of the name of it.
Is that unpacking?
Yeah.
Not quite.
you got your list and then your
Tuple being
minimum.
set to a tuple.
This is
Say that
changing
again,
the
you?
order.
It's a tuple being set to another tuple.
Yeah, but what is happening?
An
It looks like
inverse.
it's changing the order.
Yeah, just swapping.
It's
Swapping what exactly?
this.
Like if this was an XY axis or whatever point given, it would be like, okay, the Y would be the X now and X would be the Y, something like that. It's probably the worst example, but
You have generally the right idea, right? We're just swapping the values of two variables. That's all. Write this down. If you haven't figured out how to swap values of a variable, look into that. This is a really common way to do it, and then there's the other way to do it. Pretty good, handy thing to understand early on. It comes up a lot in coding challenges.
Is it
So you
kind of
just
like a, oh, I'm sorry, go ahead.
go ahead.
Is it kind of like a swizzle? So you're like switching each value one by one?
You're just
Because you're like
swapping the
flipping them. You're
values
like
of two
flipping.
variables. Yes, that's it. Yes.
When it's
Sometimes
swapping,
you have to swap values of variables to get them in a certain order. And this is just one of two ways to do it. Actually, there might be, actually, I only don't know two ways to do it. There might be more. I don't know. But yeah, this is a really common way.
when it's swapping, is it using up like a temporary space? Like, or is it just one for one, like swapping back and forth? Or is there like to hold the value? I'm saying that makes sense.
After this line, I hope I can answer this. After this line in the code, this value will hold this value, and this value will hold this value. That's all you need to understand for right now. It's how to swap values in variables. That's it. Don't overthink it. I actually don't even know why they included this in here. It's not really relevant to what you were learning, but it's fine. Have you noticed already programming is not that linear? It's just kind of all over the place. There you go. Cool. All right, so that was pretty straightforward. This hopefully you got to. If you have, you definitely have read these two. Did anyone finish reading these two things, doing the examples, and finishing this? Well, we just went over it, so I guess you're done with it. Did anyone get to all of that by chance? And that's okay if no one did. What are we missing? Where do we leave off then?
I was doing the challenges that you put in Slack.
Did you get through any of them by chance? I think that was Logan. Who was that? Whoever said that. Did you
Yeah,
get through
that
any
was-
of them?
No, I had just started when we got pulled in.
Okay, cool. This is what we're going to do. I'm going to post your groups here. I'm going to post your pairs here. I'm going to open the rooms. You can go into any room with your partner. Wherever it is that you left off outside of like obviously the short little exercise that we just did, continue with that, right? For the first 15, 20 minutes. But after that, if you have a general idea of Big O, I would like you to give the challenges that I posted in the channel a crack. There's 3 challenges, but you're going to come up with 2 solutions for each. So by the time we're finished, ideally, you would have 6 solutions, 2 for each of the 3 problems. The first note that I gave you there is brute force. When I say brute force, it's just solve it any which way you know how. That's it. Now, the second time you solve it, the optimal solution there is really important. Now, I could have chosen literally a dozen different problems, but I specifically chose these 3 for very specific reasons that I will cover when we come back together as a group. But every single one of these challenges is handpicked to teach you something really important. Does that make sense?
Who do we partner with? Are we on the list?
Posted it in the India Evening and Weekend Slack channel. All right. So I'm going to open the groups. Jump in with your partner, but once you get to your partner, if you guys need like a 10-minute break, 15-minute break, take a break for sure. All right. Open. Groups in the channel.